I welcome you all to the Spark Research YouTube channel. This is Dr. Virchandra, Assistant Professor in the Department of ECE. And in this session, we are going to take the in-semester related questions, examples, which has already been asked in the past and past years. And so these, like here, let me tell you before going ahead, these contents may be useful for your GATE exam preparation. So you may tune this here in order to prepare for your GATE examination, right? Okay, so let's take the contents here. So first of all, we are going to take the examples from the my 2025 last year. This course may be the open exam, and the total marks will be of 75 marks, and this 75 marks will be split into the two groups, right? First group, the section 1 will contain the total 7 question, right? Out of 7 question you have to solve how many question? 5 question. So actually there will be total 8 question, 7 plus 1. So from 1 to 7 you have to solve 5 question, and each question will carry the how many marks? 10 marks, right? So 10 into 5, total how much? It will be 50 marks, and the remaining 25 marks that will carry a single question, that is last one, eighth one question, right? So eighth one question means here you will have the either and or to solve, right? Means there will be the option A and B, so you can solve either A or either B. It's up to your choice, and each question will be of the 25 marks. So total you are going to write the exam for the 75 marks. Okay, so this is the pattern. There is no MCQ at all, definitely. And so let me take the questions now. We are going to take the questions, and we will also try to discuss the answers in shortly for all these 8 questions. Let's see the questions now. Okay, so here you can see the question is related to the linear, the from first unit only, linear, time variant, causal and stable. So you have to check whether these signals, actually signals are given here. So these signals are linear or time variant or the causal or the stable. What type of the signal are these? So this is the just a very simple question. So how we'll do? So first question is your y is equal to n of x of n. So n is what? So why are we writing here n? Because this is belongs to the discrete signals, right? Discrete signals, that is why we are using n, and for continuous signal we are using t, that is y of t is equal to t into x of t, right? So that is for continuous signal, but this is discrete type of the signals, right? So that is why we are using the n. Now check the linearity. So in order to check the linearity, you can use the ax1 n plus b of x and 2, and if it is equal to the n of ax and n plus b of x2, and then definitely this will be the linear, otherwise non-linear. So here you can see this is absolutely linear. Like here there is no n square, like x square or x cube, something like that, right? So no power means it's absolutely linear, no doubt. Okay, second is the time invariance. So here since multiplication is with the time, right? N. So if multiplication is with the time, so of course it will depend on the time, means it will vary with the time. So this is the time varying, time with respect to time, right? If you will remove this n, then definitely it will not be time varying. T or t square, here it is n because discrete only, n square n cube, whatever it is. So this is the time varying, and you can check it like if it is like t just shift by some time, n minus n naught, and if it is equal, then definitely this is time varying, time invariant, otherwise time varying. So here it will not be equal, right? And causality means if it depends on either present or past, then it is the causal, otherwise this is non-causal. So here nothing, present only depends, right? So this is causal only, and non-causal means the future dependency. Okay, so here then last one is the stability. You have to check the whether is this stable or not. So since this is like n of x of n, means it will keep on increasing, right? Your function will keep on increasing, so addition will be like keep on adding means like addition will not be converge. So this is not BO, right? Bounded input, bounded output means the output will never be the fixed number, it will be the infinity. So that is why this is unstable. Similarly, you can check the second and third question, right? So second one here you can see the linearity is there because there is no none x square x cube something like that, right? And then time invariance here x and x only x. There is no n or n square or n cube. Nothing is there. So this is time invariant. Then causality here n minus 1. So this is past dependence. If it is n plus 1 like here in this third one, so then in that case this will be future dependence, means non-causal, otherwise this is causal. Similarly stability, right? So here both are stable because if it is n of n or n square x square, like if it is not bounded, because here n of x, this is something like rectangular function, so you can find the total area. So if you can find the total area means the stable, otherwise if we are unable to find the total area of the signal means unstable, right? Okay, so let's take the another question now. We will move fast. Okay, so here you have to find the inverse Laplace transform for these equations. So how will you find? So very basic. First of all, write your question and then you have to write like this. See, your question is like a divided by s plus 2 and b divided by s plus 2, right? And you have to find the value of a and b. So how will you find? So you can write these equations in this way so that you can find the a and b. After finding the a and b value, what to do? You can like put again from here only, you can put it here and write like this, right? And after writing like this, it is now you can see here, this is very easy to find the inverse Laplace transform of this. And what is the inverse Laplace transform of 1 divided by s plus a? That is exponential of e to the power minus at ut. Similarly for the this one also you can get, and that in that case you will get the final Laplace transform. Similarly here again you can find like ABC and find the ABC and put that values here, and after finding the values of ABC, and then finally you can convert the inverse Laplace transform. So these are the simple steps. Okay. Okay, so here LTI system are given, differential equation is given, so h of t is given, means transfer function is given, and then determine the impulse response. So first question is that to find the very simple transfer function only. Second question, if input is given, then what will be the output? So first what we'll do, first from this equation we are going to write like in the s domain, and after writing it you can find the h of s, that is y of s divided by x of s, and then this will be the transfer function, right? So after finding the transfer function you can get the the in the time domain, so that will be the inverse impulse response, because impulse response and the transfer function both are same. Impulse response means nothing, right? Means only. Now consider the another input. So input is your t e to the power minus 2t, right? So here the input is given, so just multiply with that input. So input is this, you can convert into the s domain for easy solution, and then multiply with the h of s, that is transfer function we got, then you will get the y of s, that is output. Here also you can leave, but if you are converting that h of s in the time domain, that may be the better. Okay, so these are the steps to solve the question. So major thing is that step one, find out the transfer function. Step second, use that input just you can use the transfer function of that input, that is what is the Laplace transform of t e to the power minus 2et, that will be 1 divided by s plus 2 whole square. Why this is so? Because exponential e to the power minus 2t, that is Laplace transform, will be 1 divided by s plus a, and since t is there, so here it will be s square. So after getting the input, you can multiply the transfer function and the input, you will get the final output. Okay, so fourth question, here you have to find the DFT, right? DFT of the sequence. So here question is given, and like 2 1 2 1 2 1, like the some sequence are given, so using the DIT you have to find the DFT. So first of all you have to find the binaries like bit reversal values, and then put the values of the inputs here, and then use the 2 radix, then 4 radix, then 8 radix, and we use this w2 0 w2 1, these values 1 minus 1 1 minus 1, and then get the outputs at the different inputs, different terms, and finally you will get the output at the here, right, after adding like this all these values. So how to solve, like we have already discussed, like these there was a special session, you can check that contents. So I'm also going to show the in the detail little bit for that particular question only. So input, like see here, input are given here. These are the inputs for your bit reversal values. How to find bit reversal values, all these we have already discussed, so please check the special session on the DIT or DIT and DIF also. We have discussed all those things, right? So after getting the bit reversal values, you can get these inputs for corresponding x0 x4 all these, then put it here, and then like you have to move two radix, right? So this is the step one, two radix, and after getting the two radix at these points, what to do here, then further you can use this four radix, and then finally eight radix, four inputs, four output, four radix, two inputs, two up to down and down to up. So how to solve, just check that in the special session of the DIT DFT, right? And here, so how will you solve 4 that into 4, and here if you are coming 0 into, like here 4 0 into and here 0 plus, and 4 into minus 1, so 0 plus minus 4, so that is why this is minus 4. And here you have to keep on multiplying this minus 1, and here also you have to multiply w at 0, w at 1, w at 2, w at 3, and here you have to multiply by w40, w41, like that, right? So you can solve these questions based on that technique. Okay. Here is another circular convolution. So you have to find the circular convolution. So how will you solve? So here you can check, like input sequence. These are the input sequence are given, and the x2n is also given, right? So you have to get the convolutions. How will you get? So first you can move it from left to right, right, or right to left. So let's move from the left to right. In that case, one is there, and then the remaining it will be the at the 3 and 4, and 2 and 3 will be at the 1 and 2 will be 0. And so if you multiply like this 1 into 1, then it will be 1, and then here it is minus 1. So I will multiply minus 1 into 0, so this 0, then minus 2, and this here 0, so 0, and then here 3, and then this time you have 3, so multiply like that, then again minus 1 and then 2. Similarly, you have to repeat all these steps by 1, 2, 3, 4, 5 times, because 5 inputs are there. So 5 times you will add, then finally you will get the output 8 minus 2 minus 1, like at the each step. So this is a step 1 that we have discussed here, right? So this one 8 is a step 1. Similarly, if you will rotate by this step 2, so you will get minus 2, and here if you will repeat this step 3rd, here you will get this one. Likewise, you can solve. Okay. So here is another question related to the Hamming window. What is this Hamming window? Again, we have already discussed. You can check that contents. I will let you here. We'll talk it in a very shortly. So omega c, that is already given, and Hamming window, like for first of all, this is LPF. So low pass filter for this, and Hamming window, there is a special equation, this one. So you have to remember this equation, then only you can solve. And low pass filter, nothing. This is sinc function only as usual, and so here put the values, and you will get the h of d of n. And because we are using the Hamming window output, so how will you get? So y of n is nothing, so your multiplication of window function and plus low pass, right? So first get the low pass and then window function, and then multiply, you will get the final output. So here is your h of n, here is your window, and then multiply, and final output you will get, right? So here is the window technique. So rectangular, you can check it, rectangular and triangular, then Hamming window, this and then Hamming. So this question has been asked in this time, right? So, and Blackman also, like remember this Blackman, last question belongs to the Blackman. So we will talk about this equation, right? So this is also one of the important. Please just check it, this Blackman. I will not repeat the same slides there also. So just I will use the this equation, right? Okay, so here is another question. IIR filter you have to find using the digital Butterworth technique that satisfy the bilinear transformation. What is this bilinear transformation? Let me tell you in the just short, like the basic concept is to transform from the linear, that is your S domain to the Z domain. So that is the basic technique of the bilinear transformation. So pass band and the stop band, you can find it here using this equation here, and you can find out the cutoff frequency, and further you can get the h of s, that is transfer function, and you can also convert into the time domain, h domain. How will you do? So this is the major equation, right? So this is the main equation that you have to remember. So that is, this is the how it is being used to convert the bilinear transformation. So we will see. So how will you solve bilinear transformation? So for band pass and the low pass filter, first of all, you can check it here. These are the equations. And here we are going to use the bilinear transformation, that is S is equal to 2 by T Z minus 1 divided by Z plus 1. And what is this and how will do? And this is rack frequency also. So how will do? All these things we have discussed in our session. So you can refer to the 5th unit session, right? Okay, and so last question, I think this is the linear transformation. Again, Z transform, inverse Z transform. So how to solve the inverse Z transform? Already we have seen in the first slides, right? The first question, second question, right? And DFT also we have seen how to solve 2 radix, 4 radix, and 8 radix. We have already seen for these sequence, so you can solve based on that. Here is another question related to the linear phase filter, and length is given, and for symmetric conducting using the frequency simplified method. Here again FIR filter design. So these questions are related to your filter design. So how will you solve? First of all, find the frequency, and then you can use the symmetric. You can, like normally we are using the symmetric conditions in order to solve the questions. Why? Because all these are symmetric, right? After finding h of n, that is your window, you can start to find the FIR band stop filter using the here. This question related to the Blackman. So if you remember how to like Blackman window equation, then you can simply multiply SDN and into the WN in order to get the output, right? So this is actually the technique to solve the question. So what is this Blackman? So you can again refer to the contents, and already we have displayed one slides which have the Blackman equation, right? So technique is just to get the window with the window equation and then h of n and then multiply in order to solve. Okay, thank you to join the sessions. We'll bring one another session for the previous year question. So you can stay tuned. Thank you.